Hello everyone. Before I start to talk about the morphological operation in image processing, first I have to say that tomorrow is the career day for robotic and computer engineering program in the Institute of Technology, room number 102. And it will start at 2 o'clock and finish around 4 or 5. If you want, you can go there. That's the first thing that I have to mention. And the second thing is that today I evaluated all your assignments. Is there any one that I didn't evaluate his or her homework? Okay, if not, first, second, and third. Okay. Let's talk about the morphological operation in image processing. The topic that we discussed about them in the discourse till now was the technique that we used. The technique that we used for the grayscale image, color image, color in the color space image, and something like this. But the topic that I would like to talk about this today is just for the binary image, and it's used for the applications that use some binary image, such as, for example, fingerprinter, and something like this. Or, for example, the watermarking applications, when we want to use some watermark image, in most of the time we have to find the binary, the binary version of the image that we want to send into the host image. But let's start. Okay, let's start to talk about the morphological operation. Actually, morphological operation is used in order to find some components that use to represent some boundaries in the image or a skeleton in the image. And also it's used for filtering. It means that we can use this operation as a filter for the image. For painting and pruning, also we can use these operations. Before to introduce this operation to you, let me talk about some fundamental concept that with hypertrophy you know it from your high school or primary school. But let me talk about this. As you know, we have a definition that we call set. That is any well-defined collection of the object. We call it set. And the elements, the object that is in the set, the elements that are in the sets, we call them an object. And you know that with these signs, we can say that, for example, X is a member of the set of A, or X is not a member of the set of A. And usually we show the sets with the capital letters or uppercase letters, and we show the object or elements with the lowercase letters. And you can see easily that X, that is the object in a set of A in this example, and it's X is not an element in the set of A. And we also usually show a set like this, for example, a set of A. In a verbal, we say that A is the set of all integers from 1 to 6. And also in the mathematics form, we can show it like this. A equal, it's a set of integers of x when x is between 1 to 6. Also, we call a set as an empty set when there is no any object or elements on there. The sign is like this. Also, we have a universal set that maybe consists of 2, 3, 4, or maybe more subset on there that we show this with this sign. And we know that we can say that A is a subset of B with this sign. It means that all elements of the or all objects of the set of A also are in the set of B. It means that A is a subset of B. And also we can use the proper sign or proper subset. It means that all elements of the set of A are in the set of B, but also the set of B has more elements rather than A. It means that, for example, we have the number 1, 2, 3, 4 in the set A, and we have 1, 2, 3, 4, 5 numbers in set B. If we can say two sets are equal when one of them is a subset of another one, and also that one is the subset of the first set. Like this, I can see, for example, here A is a subset of B, and also B is a subset of A. It means that all objects that are in the set of A also is in the set of B. It means that we have equal sets. An example about this is like this. For example, we consider this set A, the object of 3, 4, 6, and B, that is object of 6, 3, 4. We can say that these sets are equal. It doesn't matter the order of the numbers are different, but the values are the same. 3, we have the 3 here, 4, 4, and 6, but just the order is changed. Also, we can say that A is a subset of B and B is a subset of A, or they are equal. And also, we can show another example here when the set of A has this object, 1, 2, the numbers, zero number or counting numbers of 1, 2, 3, 4, and 5, and the set of B is x when x is less than 6 and x is a counting number. It means that there are these sets are equal, and we can write them in this form. Sometimes a set is a subset of another set, but it doesn't mean that another set also is this subset of this set. For example, in this part, A, we have a set of A that the number is 2, and B, the set of B that the number is 2 and 5. It means that A is a subset of B because all objects or elements of the A are in the B, but B is not a subset of A because it remains number 5 here. You know that in this case we just say that these sets are not equal, or A is a subset of B. And also, for example, in this case, we have a subset of A that x is a fraction, and B is a set of x when x equal to 3/4. We know that B is a subset of A, but A is not a subset of B, and we can't call it A, we'll call it 2. And we have a sign union that all of you know about this. We use frequently in the probability. It means that the A union by B means that all objects of the A and all objects of the a set of B can go together to find the both of them. In the logic, we can call it or we can say that it's similar to the OR logic. Also, intersect that we can use for this set means that the intersect of the set of A with the B. Also, we can say a complement of the set, and we know that I did just go through it because all of you know about this. We can say the complement of the complement is equal to the original set. We can say A minus B means that it's equal to the complement of the B. A intersect by complement of the B. We can simulate these two sides are equal. For example, here we have a universal set here. We have a set of A and B. 1 to 3, the numbers in the set of A. 3, 4, 5, 6, the number in the set of B. The intersect of the A and B is 3 because 3 is in the A and also 3 is in the set of B. Union of A and B is equal to the universal set. It's 1, 2, 3, 4, 5, 6. B minus A is 4, 5, 6 because we remove the 3 from this part because it's intersect with the A, and also the B complement is 1 and 2 because we know that the universal set is like this. We remove this part and it remains these numbers. Also, we know that for example, in this case, we can say that intersect of the B with the complement of the A. The complement of the A is 4, 5, 6, as you can see here. The intersect of them with the B is 4, 5, 6. The result is the same. Also, we can show it in a Venn diagram because in the morphological operation we have to use this concept. If you assume that there is the set A and the set B, the intersection part between them are the shaded part here. For the union, we can say that we have these sets, and for the union part, what's your opinion? What's the union of them?
All of it?
Yes, all of them, because we have to add these parts to this part, and this part is the same between them. Also, A minus B. Which part we have to select for this operation?
Left middle.
Yeah. We have to shade this part. Yeah, it's remain. It's some simple operations. And also we can say that we have the mutually exclusive sets, or in some books they call it disjoint book, when the intersection of two sets are equal to empty. It means that there is no common number in both of them. And also we can call the sets A and B as a exclusive when the union of these sets are equal to another sets that we have in our universal set. And it was too easy, but as you are sleeping in this form because it was too simple. The test question: what's the result of this? The union of A with empty. A. This.
No, part of the set.
Yeah, because the set, this complement of this is the rest, and when we add this, we can find the universe universal set. And this
No.
empty set. This
No, this is A.
empty
Nothing.
because there is
No, you all of the complement.
no.
We will
No,
only
excuse me. It's a universe set because there is no common number between it because it's the set A, for example. 1, 2, 3. Okay, and A complement if we think that the universe set is like this: 1, 2, 3, 4, 5, and 6. Okay, the complement, A complement is like this: 4, 5, 6. Okay, when we write A minus this, we can write 4, 5, 6. Okay.
No, one.
One, yeah, 1, 2, 3. Sorry. No, just 1, 2, 3. Yeah, 1, 2, 3. Yeah. Yeah, 1, 2, 3. Just A. Yeah. We have no common number between these two sets. Intersection of the A complement, empty. Union of the A with the global set. Union of the
A global set.
global set. Intersection
A.
A. If A is a subset of B, the proper of the B, it's the intersection of the A and B.
A.
A. And this
B.
B. And also we can see this operation, we can say that it doesn't matter in which order we will write it. Union of the A and B is equal to union of the B with A, intersect of the A with B is equal to intersect of the B with A. And also we can say that the union and intersection are associative operations. It means that we can write it in this form, then it's equal to this form. And also we can see another example for intersect. And also we can say that this distributive laws are true for the sets. We can write in this form, or for the intersect and for the union we can write in this form. And also the answer to all this question. Again, also we can say similar to the A is an element in a set of A and not a member, and we know that's the disjoint modulus, it's the intersect of these sets is empty set, and complement and difference between them. That's the first example that we can show. For example, in these sets, if we want to find the union of them, we can say that both of them, we have to fill out both of them. This part is the intersection of the A and B. This A complement, we know that the A is this, the outer part of the A is the A complement, and A minus B, that it just remain this part. And we can say we call the reflection of the B, that we call it B hat in our work. This is some definition that we have to know. It's the reflection of B. As remember, the B has the shape of this. Because B set. The reflection of B set, that we call it B hat, is like this. And also we can write the A or AZ in this form. We add the Z that's in the scales, XXL or Y scale. We can add these two, mean that we increase the size of the A. And also we can see an example about them here. For example, if we consider this as A, it's the A complement, but not A. A and B, we can say the intersection of them, or and. In the logic we call them and. The A and B is the intersection of them. A or B or the union, in the logic we call it or. These are all parts of the sets. A, X or B, and here we can say not A and B for some logic operations. Okay, just was in the introduction about the some sets and some operation that we can use on the sets. Let's, from this slide, we start about the morphological operation on image processing. Okay, there are two fundamental operators or function in the morphological operation. The first is dilation and another is erosion. Other morphological algorithms are based on these operation. It means that to implement the other morphological algorithms, we need this function. We show the dilation by this sign, and also dilation is used to expand the image into the bigger form. In the mathematics, we can write like this: the dilation of the A and B, image of A and image of B is the set of Z, when the B hat of Z, intersection of the B hat of Z with the A is not equal to empty set. And also we can write it in this form, doesn't matter. And in all morphological operations or a function, we call the B as a structuring element. And in the example, you will see why we call it a structural operation. For example, for dilation, we have this set as a set of A. We can call it image. Later, we will see that we use this operation on the image. The size of this set is D by D, and we have the set of B, or we can call it B hat. It's a reflection of the B, but in the square we don't have any reflection. If we rotate this, we can get the same set. Okay. When we want to find the dilation of this set, we have to put the set of the B at the image, where we just need to have, we mentioned it here, just need that a part of because it has this part, this has to be a subset of the A. Just a part of just part of your structure or your set of your B set have to be inside the set of the A for dilation. Okay, if you put the center here exactly at this point, then we know that some part of this structure is outside the set of A, but we know that we have to add this structure to this. Maybe it will be better to I write it here. Okay. We have a set of A, size of A is d by d, and we have a structure that we call it set of B. The center is here, and the size is d over 4. Okay, and d over 4. Okay, if we put the center, both of them have the same. If you put the center of the structure here, because we want to start from this point, okay, means that we have something like this. Okay, then we go through this axis. Okay, here means that we add this part to the image because the relations expand the image, and also when we go in this direction, we add this part to our image. Okay, and also when we go in this direction, we add also this part because the center is here and the rest is there, and also for this part we have this. When we just go on the border, okay, we just go on the borders. Do you know what? And we know that after this part, after this dilation operation, we add these parts to the set of A, or image of A. Do you know what happened if I put the center here? After I go through the border and add these parts to the set of A or to the image, what happens if I put the center here? It means that we have in this direction. What happened? It doesn't change anything because, for example, say 1, 2, and B is 1. Okay? If we want to find if we want to add this set to this, or if we want to find the union of this set, what happened? What's the result? Union of this set. A. 1 and 2. And for this, we know that all part of the set B is in the set A, because after go through the border, the set of A is this. Okay. Then, if you put the center here, all parts of the set B is in the set of the A. It means that it's equal to A. It means that for the output, we have these parts for the A. Although we have to go through the image or through the set in this form. But at the end, we know that if we put the center inside the set of the A, when we have the B like this, means that nothing happened and we have the A. Means that we don't need go through these lines. And we know that, for example, if we want to find this, we know that this part is D, because we know this, and for this part, you can say it's d/8, d/8. Okay? It means that we expand the set of the A by dilation. You can see another example here when we have this form. This set of A is exactly the equal with this, and the structure elements or the set of the B is like this. Instead of this form, this structure element okay, we have this set, or you can call it this image, and or a structure element is like this. Center is here. Okay. D/4. Okay. The first thing that we have to do is that put the center of the structure element at this point. But it doesn't matter at this point or this point. Throw the borders or the edges of the image when we go to the inside the image. Throw the edges or throw the image. We can start off anywhere. For example, you can start from here. It doesn't matter. If you start from here, it will be like this. Okay? We know that these parts are in the set of A. It means that you don't need to add anything here because the value of in these parts is the same of the value in the set of A. Okay? The part that we just need to add is this part to the image or to the set. Then if we go throughout the border, finally we will get something like this. Okay? Then we know that we know that this is equal to D, and when we add these parts, we expand our image or set. Then from here to here we have d/2 and d/2 for these parts. Or we can write this set is dealing of set A and set B, when the set of A is this and set of B is like this. Similar to the previous one, to this example we can expand the image in this form for dilation. But where we can use these algorithms in the image. For example, assume that we have this text. Okay, this part of the text, that the letters of E and A exist, you can see there are lots of parts that's broken in the image. For example, here. If we use this structure or this algorithm for this, we can't use this one that you can see with we join the broken part because we extend the image or the edges in this form. But one thing that's different with the last example, in this example, we assume that all part of the sets are, for example, if we write in this form, it's one. It's one. Okay? Then when we go this part, it means that all these parts are one. One. Okay? But in this structure, you can see that we have one here. Okay? It means that when we have a structure like this, one, 0, 0, 0, 0. When we put this image on the original image or on the original set, we don't have to put one, for example, in this form. When we put the center here, okay, we have something like this. Means that we can't add these parts to the image, or for example these parts to the image. And you know that, for example, for this structure we have a problem like this here. You can see, if we put the center here in this part, although it joined this point to the rest of this letter, but we have a structure like this. If we put a structure that all elements are equal to 1,